Hello guys, so last video we learned how to create a custom device in the FPGA part. Today we're going to learn the basics of device drivers, okay? The idea of the device drivers is going to actually control our IP that we create, okay? But hiding the complexity to the user, okay? On this lecture we're going to learn how to create device drivers from scratch, okay? And in the end of the video, we're going to have a device driver that mimics the behavior of our IP, but in the software mode, okay? Then after this video, what we're going to do, we're going to change it to work in the Z board and control our IP core, okay? Now we're going to the board that I will explain a little bit the basics of device drivers, and then I have some PowerPoint presentation that I show a little bit with more details, all these things, okay? Hope you guys enjoyed, and see you guys in the next video. Okay guys, so device drivers basic, okay? Idea. We need to make the user think that our IP core, okay, our device is just a file, okay? In other words, we need to hide the complexity of the device to the user, okay? So the user must think, okay, he needs to think that he's actually just accessing a file, okay, in /dev, okay? We have three types of devices, okay? Character devices, block devices, and network devices. In this tutorial, we are going to pay more attention to the character type of devices, okay? For instance, serial ports, stuff that you send serially or actually in parallel as well, okay? But not in blocks or not networks, okay? So imagine here a device, okay, and you have a driver that controls it, okay? So the data input output will be done through a file, okay? But status or parameters, okay, will be handled by what we call attributes, okay? That can be with IO control or sysfs, and we're going to learn how to program this in the lab, okay? So at the end of this tutorial, we're going to create a skeleton of the device that is going to control our ALU, okay? That supports multiplication, sum, and division, and subtraction as well, okay? So the idea is just to create a kind of API or interface that is going to be used to control our IP core running the FPGA, okay? So how are we going to use this device, okay? The user will just echo a string like this, like 50, 2, multiplication, to the /dev to the device, okay? Then he's going to echo equals character, okay, to the sys class to the device some attribute, okay? A parameter, okay, you can imagine like that. And then he's just going to read the device file to get the result, okay? So basically all the complexity or like physical memory, registers, all this kind of stuff is going to be hidden to the user, okay? So the user will just echo and cut some files in the file system, okay? So this is the idea. I'm going to switch now to some PowerPoint slides that I created, okay? So there we're going to learn with more details about all this, and then jump to the lab and create some code, okay? The presentations, code, and all this is going to be available for you guys into a link or something like that that I put in the description of the video, okay? So let's start.
Okay guys, so this is just a presentation that I created, okay, to introduce a little bit more about device drivers, okay, with device trees. So learn how to develop simple module device drivers for the Zinc platform using device trees. Okay, so what are device drivers? Okay, so guys, the idea is that with the device driver, we're going to hide the complexity of the device to the user. Okay, the idea is to make the user thinks that he's actually dealing with just a file. Okay, on Linux, device drivers normally came on three flavors. Okay, for Linux, the devices are actually normally three types: character devices, okay, for instance, serial or parallel ports; block devices like USB cameras, hard disks, or network devices. Okay, in this tutorial, we're going to pay more attention now in character devices. Okay, So the majority of the device drivers extend the kernel functionality by loading them on runtime. Okay. Actually, the kernel is the Linux kernel is a monolithic kernel, but he can allow you to load modules. Okay, imagine this kind of DLLs that you actually add extra functionality to it. Okay, so device nodes. Okay, character or block devices identify using a major or minor number. Okay, so I'll not read this. I'll try to explain. Maybe it's better. What are device nodes? Okay, as I said before, the user needs to think that the device is just a file. Okay, and you have some files in the Linux. Okay, especially in the /dev. They actually are always there in the /dev directory. Okay, that make this connection between a file and a device driver who is actually controlling a real device. Okay, and actually you need two numbers. Okay, actually just one important is the major one. So in the device driver you actually register yourself with a major number, and when you create a device file, okay, a device node, you use this command mknode, okay, that you pass this major number. Okay, so next slide. So user space memory access. Okay, as the kernel and the user space exist in different virtual address spaces, there are special consideration while moving data between them. Okay, so what are virtual addresses and what are physical addresses? Physical addresses is what we are used up to now. So are addresses that actually have some meaning. They actually have a location in our RAM memory. Okay, the Linux operation system applies something called virtual memory. Okay, these have a lot of advantages. One of the advantages is actually that you can have more memory than what you actually have in the DDR. Okay, you can make the process, the user programs, thinks that they have actually more memory than the RAM itself. Okay, but this has a cost. When you are dealing accessing pointers in your programs or even in the kernel, you are not actually access physical memory. You are actually accessing memory into a virtual address space. Okay. By the way, all this is managed by a piece of hardware called MMU, which stands for Memory Management Unit. Okay. So a common mistake is to think that the kernel mode memory is equal to the physical memory. Okay. So when you are in the device driver and you have a pointer pointing to some address, this is actually not a physical memory also. Okay. So you need to have some functions that are going to do this mapping between virtual address space and physical address space. Okay. Here I just put some functions in a table. Okay, I just copied this from the internet, and in the end of the presentation you have the biography of all this. The most important for us now, a copy to user, okay, or copy from user. Okay, copy to user actually is going to copy some array from the device driver memory to the user space memory. By the way, both of them virtual. Okay, and copy from user, you're going to get some some data, some array some array from the user space to the device driver. Okay, kernel modules. Okay, as I explained before, you create device drivers, by the way, normally using kernel modules. Okay, otherwise you need to change the kernel code directly. Okay, and all the time that you need to change your driver, you need to recompile the kernel all over again. So to avoid this, you create device drivers as modules. And as I explained before, modules can be thought like DLLs that you can load on the kernel at the runtime. Okay, and by the way, the kernel modules always follow this skeleton. Okay, you have a module init, module exit, where you actually send the call, you actually point the functions that are going to be called when you load your module or when you unload your module. Let's call them callbacks, because they are not being called directly in your code. They actually is going to be called when something happens. Okay, so normally a character device driver has the following section: init, where you resist, allocate memory, and register interrupts, and exit, okay, when you detach the driver from the system. Okay, you also have what we're going to see that in next slides, the FOPS structure, okay, that actually is going to define the capability of the device driver, okay, and an interrupt routine. Okay, so here I'm just presenting the code of our character device in the old way. Okay, let me just, so these guys here are the headers. Okay, normally your device drivers will have these headers here, those two. Okay, we creating here our file operation structure, where we pass pointers to the functions that are going to handle some action in your device file. Okay, so for instance, when your device file is read, we're going to call the dev read function. Okay, can be any name, by the way, guys. When you write, you're going to call the dev write, here. Okay, when you open, you call the dev open, and when you release, the dev release. Okay, if you compile this driver here, okay, and load this driver to the kernel, the device file, okay, the device node will not be created automatically. Okay, then you need to use a command called mknode, where you actually give a name to a device file. Okay, you say that in our case is a character device file, and you send a major number and a number, in this case 1, just to indicate that you have just one device of this type. Okay, let's just take a closer look on the init function. Okay, so here the first thing that I do is call it this register chrdev. I have a number and a name. This number is actually the major number. Okay, then the functions that handle the write and the read of the mknode are quite simple as well. The first thing that I do in the dev write, okay, when the user write into a file, is to copy the content of what he wrote, okay, to a buffer internally that I have here, kernel buffer. Okay, then I said that the last element of this kernel buffer is 0, and I return this number of bytes that I received. In the dev read, I just copy the data that I had in the kernel buffer and then give back to the user. This is just the very, very simple model that is just copying back what you wrote. Okay. By the way, guys, this is an old way. You don't do this anymore because you always are obliged to call mknode. Okay. Now we on the code of the device driver, we register the device file. Okay. Device parameters with IO control. Okay. Imagine that you have, for instance, our device driver that implements a coprocessor. Okay. In our case, that's it. Is an ALU coprocessor. You send the data to this IP core, but you need also to have parameters and also status. Okay. So, for instance, you want to know if the IP core finish his processing, or you want to send a command start or something like this. Actually, everything that does not map too well to a device file itself. Okay, so almost every driver support functionality like open, close, read, and write. But beside those generic functions, every driver may have their own particular functionality, parameters or status. Okay, exposed to the user space application. Okay. There is a big disadvantage by using IO control. Okay, one of them is that you cannot have access to these parameters through the command line. Okay, it will oblige you to always create a program, which is not that cool. Okay, but to learn the basics of device files, you need to know this. Okay, so for instance, here is a user program that just open a file. Okay, my dev, for instance, a device file or device node. Actually, they are actually the same. And then we call the IO control, okay, and we use this type of command, carry set value, and you put a variable, the address of a variable, sorry. If we go here to the code, in the file operation, by the way guys, all the rest is the same, okay. What changes is now that you have a new callback and the file operation. So let's just have attention now to the file operation. Notice here that now I have a new field called unlock IO control, and I pass the pointer to my callback function, okay. And what this callback function is, just a switch that is going to verify the type of IO control that you send. In our case here is this carry set value, okay, and we're going to do something, okay. Now the new way, okay, what changes basically is that your device driver will actually ask a major number for the kernel system and register itself in the /dev where all the nodes are located, okay. So basically what you change is the init, okay. Here this function alloc chr dev region is basically saying, kernel, give me a major number, okay. Then you create a driver class. After that you create a device, and then here is where we actually create we register ourselves in the character device framework, okay. So here we call cdev init, where you pass the ops, okay, and the structure that holds our character device structure. Then you call cdev add, and this is basically the guy who is going to create this device driver for us, okay. And all the rest will be the same. You're going to have the function read and write, and actually they have the same source code, okay. Now another option to the IO control. As I said before, the IO control has this disadvantage that you need to write a program to use it. So the new versions of Linux actually came with something called sysfs, which is a directory, okay. Actually is a directory called sys, actually /sys, that is going to hold some attributes or status of your devices, okay. And the advantage of this is because then you can use your your command line, okay. For instance, echo 12 to some parameter, okay. So you don't need to have a program to test it, which is quite cool, and actually helps even more to hide the complexity of your device. So to use this guy, you call class create, as we did before, okay, device create, and the most important, the device create file. So this will be the guy who actually is going to create an attribute. So let's just check here how you create an attribute. You just call this macro here, device attribute. You say you place a name, okay. Here is going to create a file called par.crtl, okay. Here you define how your file be accessed, okay. Here I'm just saying that is going to be written. Null, we are not interested now to read this attribute, we are just interested now to write. So here we put null because we are not going to read, and you put here a callback that is going to be called every time that you write on this attribute, okay. So here I'm just putting a kernel message, okay. So when you do this echo here, you have here change attribute to 12, okay. So now let's add some logic. Basically we're going to use this code here, okay, that we register ourselves a character device and also use the attributes from the sysfs, but we're going to change a little bit to add some logic, okay. The device that we create in the previous video is just an allo, okay. I mentioned that before. that is going to implement the operations plus, minus, multiplication, and division. Okay, and we create a kind of API to access this device. Okay, and it's quite simple. You just do an echo, okay, of a string in this format. Okay, so we have one number, comma, another number, comma, an operation. Okay, so we just send this to our device character device file, sorry. Then we also send this string of one character here that is equal to the sys class 2 device par control, which is the attribute that you created, and then we read from this same file, and you should get an answer if everything is working. So now we're going to change the device driver to emulate this on software, okay? But then in the next video we're going to learn how to connect this to our IP core, okay? So first change, we just add the variables that are going to hold these operands here, okay? Then we change the guy who is the callback of that is called when the attribute is written, okay? And basically what we do, we just verify if the first character is an equal, okay? If the first character is an equal, he go to a switch, okay, that he verify which math operation has been chosen. For instance, here was multiplication, so he is going to jump to this case and he's going to calculate operand 1 multiplied by operand 2 and then break, okay? And he store this into the result variable, okay? So if you go to the next slide, when we read, for instance, when you do the cat, where it is here, when you do a cat, the only thing that he's going to do, he's going to create with an sprintf a string with the number of the result of the calculation, okay? Then he copy this to the user, okay? In the case of the write, is not that complicated, but it's simple as well. We just get the string that the user passed to us with the copy from user. Then we use the function sscanf to parse this string, okay? So here actually we put, for instance, 52 and the asterisk for the operation, okay? And by the way, this is going to be used here, okay? Then after that we have our result, okay? Next video will be about device tree, but we are not going to talk about this now, so let's stop it here. I'm going to switch to the lab to create this character device or this device driver, okay? But again, this is not going to be on the Z board just yet. It's going to be actually in our computer, and let's play and see how it goes. Okay guys, so let's start just by taking a look in our first module, okay? Let me just close all the others to don't make confusion. This one as well. So, okay, this is the real hello world module, okay? And it's quite simple, okay? This is the structure that that you have in a device driver module, okay? We just need to have these two functions here that indicate what will be the function that we start and what will be the function that will be called when the module finish, okay, finish its execution. Here is a very simple makefile that just built this guy, okay? These headers here are quite important. You need them in probably all device driver. And so let's play a little bit with this guy. So first let's call make, okay? And let's delete all the previous message on the kernel. So no message, okay? So let's first, by the way, we are not in the Z board yet, huh? So let's just install this this module here in my machine. So first module.ko, and now if we call the message, we see this message here, hello world module loaded. Okay, if we unload our module, you just boot. Cool. Sorry for that guys. It's first module.ko. I just have a typo here, and if we call the message again, we can see that this function has been called, the previous one, and this one, which is related to the exit hello, has been called as well. Okay, so now let's make the things a little bit more complicated. Let's have a look here on the second one. Okay, the make file basically is the same thing. Okay, but now what we're going to do, we're going to create a device node. Okay, actually we're not going to create a device node. We're going to create a module that accepts have a character file bind to it. Okay, so the first thing that you need to pay attention is this structure here called file operations. Okay, where you have callbacks. Okay, means functions that are going to be called when your character file is read or written to or open, or when it's released. Okay, the init, actually the exit is quite the same. The only difference is that here we call this function here to unregister our file, but the most important is here the register chrdev, which is going to create a file in our /dev directory. Okay, with this major number here, 90. Okay, and here are the functions that are actually the definitions of the callbacks that you create. So dev open, actually we don't pay too much attention, but dev write and dev read, yes. Okay, so basically this function will be called when your module is when someone, for instance, write into your device driver file. Okay, and the first thing that it does is just to print a debug message, but then this function here, copy from user, actually this function here is going to populate a kernel. Okay, let's call it curbuff. Okay, with any data that come from the user space. Okay, in this case, for instance, if the guy writes something to this file, this string, this something that is being written to this file is going to be placed in buff. Okay, in this variable here called buff, and then we're going to copy to this internal array here. Okay, and then we just return the number of the number of bytes in this string. Okay, here we just put that the last element is 0, and then we return the size here. Okay, now for the read we call the function. Previous was copy from user, which means get something from the user space to the kernel space, and now we call copy to user, which actually going to copy something to the user space. In this case is we're going to copy to this array called buff, our which is a destination, our kernel buffer. Okay, so basically this is just a look back. What you write is what you actually, what you read is what you write. Okay, so let's just execute this guy. Let me just go to this directory. In this case, workspace second. Okay, let's just make it again. Oh, sorry. So let's create our node. Okay, let's say that his name can be char second. Okay, is the type character device. Okay, probably need to call this with sudo, and the major number will be 90, and here we say 1 because will be the first device, for instance. Okay, say that this file is writable, actually writable and readable. okay? And let's just clear and write something to it. So echo something in /char second. Okay? Here we can see that the device was open. We wrote something. Let's go here to the function, to the callback that handled the write. So this was executed, okay? And now, actually, if we do a cat on this guy, something funny will happen. We're going to read, but as we always return the number of bytes, and we never return 0 here, we're going to read what we wrote like forever. You see? If I come the message, you see this as well. Okay? So basically, when you want to stop your read, you need to return here 0. And we're going to see that in other videos. Okay? So, second module done. Let's see the third. Okay, what is the difference? So, this one do something different. Instead of creating the node by hand, okay, like before that we called MK node, we use a different way to register a character device. So before we have to call this function here, here in the init, register chrdev, and now if we go here to our init hello, we create a class, then we create a device, and we call this function here cdev init, and this one will be responsible to create the device driver for us automatically. So no need to call mknode again, which by the way is the new way to do it. And all the rest is the same. We have the read and the write callback, okay? And actually we didn't add any logic to it, so it's basically the same. Okay? So maybe let's play to see how this guy is working. So let me close this guy. Let's do ls mod just to see how many modules we have, because I think we have a lot already. So we have probably we have the second module. Let's remove this module. Let me check if we have. No, we don't have the first module. So fifth module. Okay, we have too many modules here. Let's take out some of them, otherwise we're going to be lost. Okay, so let's go to our third module and type make, and let's install it. Sudo mod. Okay, the difference of this guy is that if you come here to /dev, we can see that probably we have some guy here. So let's check. Here, truth device. Okay, so basically this guy has been created here in the device, actually here in the cdev init. Okay, and this function here, allocate region, is the one who actually create the major number for you. So actually you ask the kernel to give you a major number, okay, and then with this major number we just initialize this character device. Okay, so this is actually the better way to do it, because then you are not obliged to run mknode again and again. Okay. Okay, guys, so this is the last module, okay, that actually we are going to work this still in our computer, okay. This is not meant to run on the Z board yet. And here we're going to actually start to create the logic of the device driver that we really want to do, okay. So let's first just scroll down here on the init, okay, just to remember again how things go, okay. So first thing, we call this alloc chr dev region. This guy will be responsible to give us the major number, okay. Then we create a class, okay. This class is going to be part of the sysfs, okay. Here we pass the name of the module and the class name, okay, which is class tut, can be anything that you want. Here we create a device, okay, with the function device create. After that, we actually initialize, let me just put a comment here, initialize the character device, okay. This guy will be the one who is going to be created in /dev, okay. And these two functions here, device create file, okay, are the ones that are going to create an attribute on our sysfs, okay. So attributes on sysfs actually is in /sys/class. The name of our class was class tut, something like this. The name of our device, and then you're going to have two files here, par control, okay, and this busy, okay. These files are attributes that are defined here. Let me just look at them and found here, okay, with this function device attr, okay. Basically here we say the name of the attribute, okay. Here we actually configure the permission of the file, okay. So this is going to be write to the user, okay. This is going to be read to the user as well. Here is a callback that define what will happen when this function is read. Here is what will happen when this function, when this attribute, sorry, is written, okay. Here the same thing, but actually we have just one attribute is busy that is only read, so we just pass this callback. And here is going just to create a string response saying busy is 0, okay. And in the case of the write of the par control, is actually the guy who is going to parse the mathematical operator of our ELU, okay. So basically when this attribute is written, this callback will be called, okay. And the first thing that we do is we verify if the first character is equal. So if it is, he's going to do a switch case in math operation. So if it's plus, we're going to calculate operand 1 plus operand 2. If it's minus, operand 1 minus operand 2, multiplication and division, okay. And then we just print the result, okay. These operands are going to be populated, okay, on our write callback of our device file, okay. But we're going to go there. So let me just scroll down on these guys. So we have here a callback called dev write and dev read. So basically this guy will be called when the character device file is read, and this guy when it's written, okay. In the case when this file is written, we're just going to parse the string of the type, for instance 2, 2, plus. So this will create 2 plus 2, okay. So here is this sscanf is just to parse this string, okay. And after that I just print, okay. Actually I populate these variables here, operand 1, operand 2 and math operation, which are the ones that are used down, up here, okay? And after this is written, okay, after we select these operands here, the user is supposed to send to the attributes the equal, okay, and then at a later time read, okay. And when he read on the file, he's just going to we're just going to create a string, okay, with the result that from that operation, okay, which again is calculated here, okay. By the way, when we do this in the Z board, this is going to be done through our IP core, which basically do the same thing, okay, that calculate plus, minus, multiplication, and division. Okay, guys. Again, just to remember, this structure here, defines which callbacks to handle the character file. Sorry, I'm saying device, but it's file. Okay. This structure is used here in the init. No, where is? Yes, here. Okay. So basically here, when you do cdef init, we initialize our device file. Okay, we initialize our device file and we pass those callbacks. Okay, so basically those callbacks will be called when the whole thing works. Okay, so let's save it. Okay, here we are in the directory of this project. Okay, so let's call make. Okay, so guys, let's install this this last module. Okay, so sudo ins mod and the name of our module. Okay, just give my password. If I now put dmessage, okay, we have here as last message our module that has been loaded. Okay, let me just clean this guy so we have a clean one. Clear. Now let's play with our driver. Okay, so first, if we do ls dev to device, let's put ls -a. Okay, we have this device driver, which are our device driver that is automatically created when you load our module. Okay, let's just check which are the access here. So in this case, right now we cannot write to it. So let's just change it all to plus write and read and write. Sorry. So we're going to be able to send some stuff and read data on this guy. Now let's go to our /sys/class/ class tut /tut device, and we see here that we have now this is busy and these par control attributes. Okay, let's just remember again where they come from. They are okay, they are here. Okay, and now let's play with our guy. Okay, so let's clear. Let's calculate, for instance, 50 multiplied by 2. Okay, and we send this to our /dev/to device. Okay, if we run the message now, you see that he detects this math operation. Okay, now let's send this character here to /sys sys class tut to device par control. Okay, and these are the guy who is going to calculate something. Oh, sorry, forgot to change the property of this file as well. Change mode, all plus read and write. Also we do this to the is busy. Okay, so just to remember, we send something to our driver. Now let's ask him to calculate something. Let's send this. Okay, by the way, when this happens, he's going to jump in the switch case here because the first character is equal. Cool. Now let's just do a cat in /dev/toDevice. Okay, so here is our result. If you do the message just to see the last kernel messages, we can see here. See, here is the point where we send the data to the character file, character device file. Here is when we send the equal, okay, and then he calculated. Okay, if we do a cat again to this file, we got nothing. Okay, basically we created in the read if response ready, we send something. After we send, we put this guy to 0 and it will not execute again. Okay, but if we, let me clear, if we calculate something else, like I don't know, division equal 5. Okay, let's play what happened if you divide by 0. But by the way, guys, this I don't know, something nasty will happen. I simply didn't know. I just thought about this now. By the way, is your actually is the device driver creator responsibility to handle these cases? Okay, let's do equal, and poof, something nasty happened. Let me just open here again the console just to see what are the error message. Okay, so we have our module here that just crashed. Okay, so guys, this is the last part of this tutorial. Okay, the idea is really to learn how device drivers work. Okay, and we created the skeleton that is going to be used later in the Z board. Okay, so hope you guys enjoyed, and if you guys like, give me a thumbs up. See you guys in the next video where we're actually going to put this to work in the Z board, and this guy here is actually going to send some data to our device in the FPGA part. Okay, see you guys. Ciao, ciao.